All right. I will begin with a word of prayer. Sorry if I'm giving you false hope of a pizza final.
There will always be hope. We'll bring this up in like a month.
Take this energy and put it into doing mission 2. Let's see here. There you go. All right. I will begin. Dear Father, we thank you for this day. I thank you for these students. Just ask you to just guide our work today and help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me erase this unpleasantness. There we go. And talk about methods. The method, it's called separation of variables. And so I'm going to illustrate by example. All right. So example 1. Suppose you're up against dy dx equals to, I don't know, minus x over y. You want to solve this differential equation. How do you do it? The answer is, so basically this separation of variables is a two-part thing basically, right? Step number 1, separate. Step number 2, integrate. I guess there's a third step. If desired, solve for y. I guess there's a step number 4. If needed, impose initial condition. And I'll show you that, in fact, we can build the initial condition into the integration step if you want to. But one thing at a time, okay? So, all right, separate, first of all. So that looks like this. We've got y dy equals to minus x dx. I have separated the variables. You see why that's called separating them? Not especially surprising, right? Put all your x's on one side, all your y's on the other, and then integrate. So you're like, I can do this. 1/2 y squared equals to minus 1/2 x squared, and got to add a constant, right? There you go. At this point, I could put a box around it and say, done, right? This is a general implicit solution. It's a general implicit solution to, let me give this thing a name. I'll call it star. Any questions?
I feel like there's a catch.
No, it's really just that. It can be easy. Now, let's, example 2. Let's solve. Same differential equation again. Dy dx equals to minus x over y. With initial condition y of x naught equals to y naught. All right. Now this is entirely equivalent to saying solution curve goes through x naught comma y naught. All right. X naught and y naught are arbitrary, but given numbers, okay, for this problem. Now there are 2 paths we can go down here. All right. The one path is just to use example 1. All right. Just to use example 1. And if we do that, what will we do? Just plug it in, right? Like we've got 1/2 y naught squared equals to what? Minus 1/2 x naught squared plus that constant. Now we don't know what the constant is, or we didn't know what it is, but now we know what it is. What is it? Not 0. I didn't say x naught is equal to y naught. What's it? So c would be equal to 1/2 x naught squared plus y naught squared. Yep.
What does x naught and y naught stand for?
They are a given but arbitrary point. So just a point. Yeah.
Why are x naught and y naught squared in this?
I'm using this formula right here we derived. I'm plugging in the point x naught, y naught, and seeing what c is needed to go through that point. So, like, okay, so what's that? No, no. So we have 1/2 y squared. I mean, I'll write it out what this means. Minus 1/2 x squared plus c. Now we just figured out c is what? 1/2 x naught squared plus y naught squared, yeah? Putting it in. And then let's clean this equation up. I mean, it's pretty obvious what it is. If you add all the variables to one side and leave the given but arbitrary constants on the other, what do you get? You get x squared plus y squared equals to x naught squared plus y naught squared. That's a nice way to write the answer to example 2. And it's very unsurprising, because if you go back to example 1 and you clean this up a bit, what this is really saying is that x squared plus y squared is equal to 2c, I think. Yeah, x squared plus y squared is equal to 2c. And you might recognize this as a circle, right? Radius what? Square root of 2c, yeah? Centered where? The origin, yeah? So of course, if you want the circle, right? So how many solutions are there to this? Yeah, lots of them, right? Any circle concentric around the origin is a solution to this differential equation. Different choices of c correspond to different radii for your solution. And what example 2 does is it says, if you want to pick out, you know, the particular solution curve that goes through this point, let's call it x naught, y naught, well, the equation of this circle is exactly that, because the point x naught, y naught is on that circle. Now we could put x naught equal to 1 and y naught equal to, you know, 3 or something, and you could find, you know, specific numbers, but I wanted to do it with variables for a second here, because I wanted to show you the other method. What's the other method? So this is method 1, which is solve it like generally and then put in the initial condition. The other way you can do it is you could build the initial conditions into the integration. So like the other way to do this is method 1. Option 2 looks like this. So we go back to we had what we had. We take our dy dx equals to minus y over x. We separate. Oh man, that was x over y, wasn't it? We separate. You got your y dy equals to minus x dx. And one of the things you could do here is just integrate both sides. Say integrate this one, let's say from y0 to y1, and correspondingly integrate this from x0 to x1. And if I do that, what I'm going to get is 1/2 y1 squared minus y naught squared equals to minus 1/2 x1 squared minus x naught squared by the fundamental theorem of calculus part 2. And then, since I've done that for arbitrary y naught and x1, I might as well do what I usually do, which is, okay, so we're going to let xy equal to x1, y1 to get, that gives us, you know, 1/2 y squared minus, my bad, y squared minus y naught squared equals to minus 1/2 x squared minus x naught squared. So we've already built the initial condition in, you see. You can solve this equation and you'll get right back where we got to, namely x squared plus y squared equals to x naught squared plus y naught squared. So another way to build initial conditions in is to integrate. When you separate, you actually integrate over a pair of points, and then you can make one of those points variable that you're interested in, x comma y, and make the other point the initial condition that you're trying to fit. And if you do this, well, then you don't have to, you know, it just automatically builds the initial condition in. Now, I don't usually do this. I don't usually do option 2. Usually I just find the implicit general solution, and then I find the c that makes it work. That's just my usual approach. But this is something should be mentioned, and now I've mentioned it. Example 3. Unless there are questions. One of the things I'd like you to notice is like the solution curves here, right? How do they differ from the differential equations that we've solved before this point? What was the relation between antiderivatives, right? If you're you know, solving, for example, dy dx equal to, oh, I don't know, x, right? We don't need separation of variables for this, right? I mean, you can, if you want to, you can separate variables. What's it look like? dy equals to x dx, right? Integrate both sides, what do you got? Y is equal to 1/2 x squared plus a constant, right? In other words, really what we're doing here is the integral of x dx is equal to y, right? That's the function that when we differentiate, we get back to the integrand of x, right? 1/2 x squared. How do these look geometrically? Like, what's the difference between the general solution set to this versus the general solution set to my first example? They're really, really different. These are what? Parabolas, right? And they're just kind of boring. They're all the same, right? If you've drawn one of them, you've drawn all of them, right? I mean, they're just, it's the same shape. Done what? So they're just related by vertical translation, right? And that's why it's okay to add the constant at the end, right? It's not okay to just ad hoc add the constant onto the end here. You have to add it when you separate the variables. You can't like not add a constant, solve for y, and then at the end of your thought process, oh, I'll just tack on plus y. If you do it, you won't be right. Over here, you can do it because, you know, the general solution, how you get other solutions from a given solution, it's always just adding a constant and shifting up and down. But that's not the case for like more interesting differential equations. Yep.
For example 3, when you took the integral, why did you just take the integral of dy? And in example 1, you took the integral of y dy.
I don't understand question yet.
Well, I know, but it was dy over dx, and then you took the integral of each side.
Oh, well, you could think of this as separating variables. I multiply dx to the other side. That gives me dy is x dx. And then go from there. But you could also think of it in terms of just like, you know, here you could just integrate the equation too, right? You could also think of this as, well, I'm integrating dy dx with respect to x. Yeah?
So you're multiplying the denominator to each side.
I mean, this problem in particular, you can directly integrate both sides with respect to x. And when you do such, the net change theorem gives you back y, like that. We can't usually do that. Like, I can't do that in example 1 because I don't know why. I mean, I can't. Anyway, example 4. What if we're up against dy dx equals to, oh, I don't know, let's say x plus e to the x over, oh, I don't know, y cubed plus y to the 4th. I want to find the general solution to this problem. What do you do? Separate, integrate. Good answer. There's low-hanging fruit here. I'm going to pick it. Very good. Yes. Let's see. Y cubed plus, I like it, y to the 4th dy equals to x plus e to the x. Come on. So then we integrate both sides, what happens? I get myself a 1/4 y to the 4th plus 1/5 y to the 5th equals to 1/2 x squared plus e to the x plus a constant. All right, so at this point, I would point out in retrospect, we could have solved for y locally in examples 1, 2, and 3, right? Well, in fact, example 3, this is just straight up an explicit general solution, right? We have y as a function of x. Now here, I don't have the, example 2 and 1, I don't have y as a function of x, right? But it wasn't that big a deal to solve for it either, right? You can isolate y squared and take the square root of both sides. Then depending on whether where you're looking is positive or negative for y, you'd either choose the positive or the negative square root as appropriate, right? You can locally solve for y here with not too much trouble and so find the explicit solution. I personally cannot solve that for y. I don't know if you can, but I can't. Can you solve this for y? But that's a solution to the differential equation nonetheless. But it's what we call an implicit solution because, again, I can't solve for y. So a lot of times, I'll ask you guys in this material just to find me an implicit solution, which would mean something like this. Now, you could still fit an initial condition, right? If I wanted to find the implicit solution through, you guys give me a point, any point. Well, I should be careful, not any point. Let's not put y equal to 0. That seems like a bad idea. So like if I want solution through, let's see here, let's pick a point. I don't know, 1, 2. Then how do I do, what does that tell me c is? I plug this point into the general solution, and what do I get? I get 1/4 of 2 to the 4th plus 1/5 of 2 to the 5th equals 1/2 of 1 squared plus e to the 1, also known as e, plus a constant. And so solve that for c. And plug it back in here, you have the implicit solution to the initial value problem. It's not, doesn't, that's it. Shall we work another? Let's work another. I shouldn't have erased that. So I think if you've looked at your homework, which I would encourage you to do sometime soon, understandable if you haven't yet, right? Because I didn't really cover these methods Friday, did I? I just kind of showed you how to visualize these things, which is not the same as finding these formulas, is it? So, but now that we're starting to do this, you should be able to do a good chunk of the homework. By tomorrow, I think I will have shared with you pretty much all of the skills that you need to solve the homework, and we'll just be doing examples the rest of the week pretty much. So just to give you a flash forward, but as you're solving the homework, what you're going to find is that the separation is easy, but the integration is more of the integration you still need to work on, yeah? So there's a good bit of harder integration in the homework integrations. Let's see here, I'll try to do one like that. Example, 5, my bad. Here's one. What if we're up against, let's say dy d theta, ooh, d theta, tricky. Let's see here, is equal to, I don't know, let's say sine squared theta divided by cosine cubed y. So let's find the solution to this guy. So we separate. And we integrate. Yeah. By the way, if you're wondering the mathematical justification of what we're doing, it's really just U substitution. It's the theorem of U substitution. It's the change of variables theorem. And it's just, this is how the notation works out. The unreasonable effectiveness of the differential notation is what's at play here. But now these two integrals I'd like to do separately, not at the same time, yeah? So let me call this one 1. Let me call this one 2. Now 2 I guess I can do right here, right? That's the integral of 1/2, 1 plus, plus? No, minus cosine 2 theta d theta, which we integrate to theta over 2 minus 1/4 sine twice theta plus a constant. There you go. That's the integral of the right-hand side. How about the left-hand side? How about 1? We've got integral of cosine cubed y dy. So what I do is I rewrite that as 1 minus sine squared y times cosine y dy. I make a, this is going to be minus du. I'm going to make this u equals to a minus du? No, that's a plus du, my bad. So I make my u equal to sine y. And so with that substitution, what you're up against is the integral of, you're up against the integral of 1 minus u squared du, also known as u minus 1/3 u cubed plus a constant, but you got to put back in your u. So we got ourselves the sine of y minus 1/3 sine cubed y plus a constant, and yeah. So the general solution then looks like sine of y minus 1/3 sine cubed y plus a constant equal to theta over 2 minus 1/4 sine of 2 theta plus a constant. Oops. I don't need two constants here, right? I mean, you call this C1, you can call this C2 if you like. We don't need a C1 and a C2, right? Like, just keep one of them. You know what I'm saying? If I put a C1 here and I see a C2 here, I might as well just absorb them and call them together collectively on one side or the other, just C1, just a C, right? So essentially what I'm saying is, you know, subtract C1 over to the other side, right? Then you'd have what? C2 minus C1, right? Some of you are bothered because I flipped my labels here. Let me fix that. That should be 1 minus 2, right? If I stick with my what I have right above it. C1 was, the 1 was with the theta, the 2 was with the y. So if I move it to the other side, I've got this constant C1 minus C2, but think about it. It's completely arbitrary. So why keep it as two constants when just one will do, right? So you just take this and you say, well, I'm just going to call this C. And I lose no generality in doing that, right? So we just, and there you go. Put a box around it. That's your implicit general solution. Again, if you could solve for y, you're more of a Hokage in pre-calculus than I am, that's for sure. Like, good job if you can solve for y here. I mean, I could locally solve for an approximation of y, but that's not this course. Well, maybe later. All right. Are we good so far? Shall we do more? Let's do more. All right, so example 6. Let's work out dy dx equals to, I don't know, y minus 2 over x plus 3. See if we can do this one. So we separate. That gives us dy over y minus 2 equals to dx over x plus 3, right? and then integrate. What'd you guys get? Oh, log, natural log of the absolute value of y minus 2, right? Equal to what? Natural log absolute value of x plus 3, right? And then plus a constant. I mean, we could add on either side. So the point is you can add a constant on both sides, right? Or you could add a constant on one side and just accept that you're always going to implicitly go through the thought process we went through back in example 5, where we have a different constant on both sides and we collapse them into one constant. So rather than saying this every single example, we just add constant to one side, all right? That's what we do. Now, if you just wanted an implicit general solution, we're done. Hooray, you got it, right? Here we go, implicit general solution. That's not quite true. I'll put some quotes on that, because it's not quite true. It's not really general. What's the one failing of separation of variables that I haven't really fessed up to yet? The domain. It is a domain issue. Yeah, that's true. So we're doing what? The initial equation. Would y equals to 2 be an acceptable solution to this differential equation? I have some votes for yes, some votes for no. Who will win? So yes, I think it depends on which line you're looking at, right? Y equals 2 is definitely persona non grata here, right? Like, no, you can't do that. No, 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 no. Division by 0. Yet up here, if I put y equal to 2, identically so, no problem. Right? And in fact, y equals, think about it for a second. Y equals 2 is a horizontal line. dy dx is 0 for that. 0 equals 0. It works, right? Y equals to 0 is what's called, rather, y equals to 2 is an exceptional solution. Exceptional solution with regards to the method of separation of variables, right? The method of separation of variables has lost that. All right? You can't you can't get y equals to 2 from this. All right?
So there is a catch.
There is a catch, yeah. But here's the funny thing. Here's the funny thing. Is if you find the explicit solution, you might accidentally put the exceptional solution back in. So let's go the next step. We're not going to be, if desired, solve for y. Let's do step 3. Okay, we're going to find the explicit solution. Solve for y. How do you do that here? Yeah, we'll take the exponential of both sides, right? So exponential of this equals exponential. Well, let me use the notation. So we could do this, but listen, guys, I can either write like that or I can write like this. E to the, just to warn you, I use both notations, so I'm just trying to introduce you to this EXP notation is useful if you want to make the font size bigger in the input. But anyway, so we have this is equal to e to the natural log absolute value of x plus 3 plus a constant, right? Now we can use properties of the exponential to rewrite this as what? E to the c times e to the natural log of the absolute value of x plus 3. All right? And then what? Well, then we should use properties of the log and the exponential, right? As their, I mean, the log is by construction the inverse function to the exponential, right? So what we're looking at here is absolute value of y minus 2 is equal to e to the c times the absolute value of x plus 3. Now think about this logically. If you have absolute value equals absolute value like this, you can summarize all of the possible contingencies by just writing what? Y minus 2 is equal to plus or minus e to the c times parentheses x plus 3. Because either both sides match and they're positive, or both sides match and they're negative, or one is the negative of the other, or they're both negatives, so you can cancel the minus out. Anyway, plus or minus covers all your bases. But then, here's the thing. Plus or minus e to a c, well, that's kind of an awkward way to write a constant, right? So why not take this guy and call him what? Well, we'll just call him k, right? Or better yet, m. After all, that's what it is. It's the slope, right? And you've got y is equal to 2 plus m times x plus 3. So it's kind of funny, but if you do the algebra, right, and you forget about where the m came from, right, m equals to 0 is entirely reasonable. Because m equals to 0 is what? M equals to 0 is the y equals 2, right? But if you think about it for a second, m is plus or minus e to the c. So in terms of what the logical flow here, is m equals to 0 a reasonable value for your constant? Well, it's not, right? Because the m is plus or minus an exponential. But for other reasons, separate from the separation of variables, just going back to base principles at the start, we see m equals to 0, which is the y equals 2 solution, is in fact totally legit to throw in. This happens a fair amount when you're solving for y. So the strings attached are just this. After you separate variables and find your explicit solution, you have to take a second to go back and look at the original equation to make sure that you haven't inadvertently, put in something that violates the original definition, like domain of the differential equation. Every differential equation has a domain, In other words, the values which make the equation reasonable. Like, what's the domain of this differential equation? Well, I better not put x equal to minus 3, right? This differential equation doesn't quite make sense at minus 3, so for x. So what do the solution curves look like for this one? We've got, they're lines through what point? Well, they all have a y-intercept of 2, that's true. And let's see here. They have the point what? Minus 3, comma what? If I plug in minus 3, what do you get? 2, right? So they all go through this point, minus 3, 2. That is common, independent of your choice of m. For all possible m that points on the curve. So what you're looking at then, minus 3, 2, right, are lines through this point of all different possible slopes, right? So, and I suppose to be picky, the vertical line is thrown out, right? As we formulated the differential equation. But that is kind of an artifact of just how we've stated the differential equation. If you want the vertical line to get back into this problem, you can take this differential equation and you can write it in its so-called Pfaffian form.